Hello, and welcome to the second video lecture from section 2.2 in the book. In this one, we're going to be talking about how to actually solve separable equations. So in the first video, we talked about what it means for an equation to be separable and how to identify it. And this one, we're going to actually go ahead and go through the general method of solving these sorts of equations. So let's go ahead and jump on into that. So like we said in the last video, an equation is separable if you can write it in this certain form. M of x plus n of y dy dx equals 0. So we're going to assume we have an equation that's in that form and look at how we want to go about solving it. Now, this is one of the first methods we do, or first ways. So this is the first method we're going to attack for solving differential equations because it's fairly straightforward and kind of makes sense in that you're trying to undo a derivative by taking an integral. So the method of solving separable equations is one of direct integration. It's one of the two that we'll talk about that use that. It's this one and section 2.1 about first order linear equations, which you solve also by direct integration. The idea is basically I want to integrate some functions and use that to find the answer. So how are we going to do this? Well, let's integrate the functions m and n and give names to their antiderivatives. So let's say that we have a function h1, this is the same note used in the book, of x, such that h1 prime is m of x, and I have a function h2 of y, such that h2 prime is n of y. How would I find these? By just integrating m and n. They're functions that will be given to me. I can just integrate them and get antiderivatives for them. But now if I have this, what do I know? Well, I know if I take d dx of h1 of x, I just get m of x. All right, that's how it's defined. What happens if I take d dx of h2? Well, I'm going to get n of y because it's a derivative, but then I also have a chain rule term, right? Because the function in terms of y, but I'm taking a d dx, so I'm also going to get a dy dx that pops out. Now this looks good because I have m over here and n times dy dx over here, which means then that d dx of h1 of x plus h2 of y equals 0. It equals 0 because it equals m of x plus n of y dy dx, which is right up here at the top. It's exactly what we have here, so it equals 0. But now if I have a derivative equals 0, what does it mean? It means the thing inside equals a constant. And again, we have this arbitrary constant c showing up, which we would expect because we haven't picked an initial condition or anything yet. So this is a general solution with this value c. So that's how you go about solving these equations. You just find antiderivatives for the m and the n, and you get a solution of this form here where it's h1 of x plus h2 of y equals some constant. You will then pick the constant based on the initial conditions by setting the values to where it's supposed to be and see what comes out. However, there was one main assumption we had to make when we were doing this. Up here, we said we could take the x derivative of this function to get this. What that means there is we need y to be a function of x. Now what that causes issues with is what happens if dy dx goes to infinity? Well, if dy dx blows up, we're going to get a vertical tangent, which means y is no longer going to be a function of x. And that's going to cause a solution to break down and no longer exist. That gets seen basically because these solutions here that we get are defined implicitly, right? We don't have y equals a function of x at the outset here. We have some relation between the x's and y's, which may not give you curves that last forever. So let me give a quick example of that, and then that'll be it for this video here. So let's say I have this ODE, which I've already written for you in separable form, right? You can solve this ODE. Let's go ahead and solve it out real quick. So I need to find antiderivative for the x function. So my h1 of x is going to be x squared over 2, and my h2 of y is going to be y cubed over 3 minus 4y. Make sure you know how I got those two functions. It should be clear. You should know how that works. Just make sure you can follow that. So then my solution is x squared over 2 plus y cubed over 3 minus 4y equals some constant c. And the constant c depends on initial conditions. Now, you would think this means that just things can go forever and there's no issue with it. However, there are problems where this term vanishes, right? Because if I were to solve for dy dx, I would get dy dx equals x over 4 minus y squared. Now that has a problem when y is plus or minus 2. Now, to show you what happens here, I made up a maple thing that talks about what's going on and shows this equation. So let's go take a look over at the maple. All right, so here is the differential equations we had on the previous page. Dy dx equals x over 4 minus y squared. That's the equation we have there. Maple tells us it's separable, which is good. We knew that. And we can solve it. And as you can see, we have the same equation they did. We got 1/2 x squared plus 1/3 y cubed minus 4y equals constant. It found the constant more explicitly, but that's fine. And then we can look at what happens at certain values. So we draw this graph, and you can see an issue here. Say we start at y of 0 equals 1. So it means we're on this curve here at this point right here. As we flow, we move forward, but then we hit this point here. What happens is we can't go any further. Why not? Because we've reached a vertical asymptote here at y equals 2. So our solution would not be defined past this point in terms of y as a function of x. If we were defining things like a system, like we'll talk about much later in the course, we might be able to go all the way around. But for what we have right now, we're defining y as a function of x, and so we can only go up to here. We cannot go any further. We stop at x equals whatever this x value is for y value equals 2. If we had started at y equals 0, we would flow this way and go, and then stop again because we hit a vertical asymptote point here. So y equals 2 up here causes us problems of that form. Y equals minus 2 is a weird situation down here where it looks like things are splitting. That's because at this point we actually don't have uniqueness. If we look at this point at y equals minus 2, we don't know what the solution is going to do. It could go up, it could go down. We're not sure because there's no unique solutions when the bottom here breaks down. So the solution stops at vertical asymptotes and has other weird problems when you hit points like -2 here. So even though 4 minus y squared, smooth function, x, smooth function, the solution can still break down at some value of x that's not infinity. And that's a unique characteristic of nonlinear equations. So it breaks down at the vertical asymptotes, and you could find the x values for that by plugging into here, but they'd be complicated to find. But at y equals 2, you get the vertical asymptotes and the function stops there. So that's sort of a basic idea of how we solve these equations and the issues that could arise with solutions existing beyond certain points in x or time. I'll give you one example here that you guys can work on to solve of a simpler separable equation. The next video in this set will just be going through examples of how to solve these equations. So if you want to look at that first, then come back to this problem, you're welcome to do that. But I'll go ahead and write that problem up for you right now. Also, as a fair note for these problems, you are allowed to leave your function as an implicit function, right? You don't have to solve for y as a function of x if you can't, or if it's hard or you can't or you don't want to. You're allowed to leave them implicitly. If you can, do it. If it's easy, do it. But in a situation like this, you're going to end up with a y squared here. You have to solve it out. You might as well take the square root. But if it's more complicated than that, you would not have to. So keep that in mind when solving these and other separable equation problems. So there's that problem for you. Solve it, put it on the worksheet, and turn that in tomorrow in class. Thanks a lot for watching, and I will see you in the next video.